Alright, well, hopefully you enjoy that little intro video. It's drone footage of the Okmulgee River a few years ago. Hopefully, you know, we can be out on the river again soon, but right now don't get that close if you're out there tubing. You gotta have 6 feet apart. Alright, so I assigned comparing probabilities for this week, and I really like this because it's kind of, alright, let's try to talk about probabilities in a real life scenario. And the first thing we really need to think about is probability is on a chart here. Basically, how likely is something to happen, right? That's really all you care about. And you've got 0% or 0, you got 0.5, and you've got 1 right here, which is really 100%. Absolutely, that is certain, right? That is 100%. 50-50 is as likely as not. I talked about that in another video, and that's really just a coin flip, right? It could go either way, and 0 is impossible, right? Never going to happen, can't happen, and impossible to happen. Okay, and there's a lot of good solutions for that. But a lot of our probability lands in between impossible and certain, and a lot of times it's going to be anything greater than 0.5 or 50% is more likely to happen. Okay, so the odds are more likely. It's better. If it's less than 50%, it's less likely. That's all it is. Right? We're not trying to be super confusing here. But the coin flip, and I love the coin flip, is really the epitome of the 50-50, right? So you have two sides, and you can only land on one side at a time. You say heads or tails, it could go either way, right? It's really, that's why they say when you make a decision, where are we going to eat tonight? I don't know, flip coin. All right. So, but as we get above 50%, you start realizing that things are more likely to happen. And then when you're less likely, you're more of an underdog. And I talked about that in another video. So let's take a look at this problem here. I think it says Ike is sitting there um, deciding whether, let's hide this, deciding whether to take his girlfriend on a dinner date or a movie date. The probability of his having successful dinner date is 55%, and the probability of his having successful movie date is 0.45 or 45%. And so we're really saying what is more likely to occur here. So the first one is over here. It's 0.55. Oops, let me write. It's 0.55. So it's above this 0.5, so it's more likely to happen. And the movie date is 0.45. It's not saying that it wouldn't be a successful date, but it's just less likely. So which of these events is more likely to happen? Well, the one that has the higher odds. And what was that? Well, that was the dinner date. So let's see if there's a good answer here. Likely to have a successful dinner date? Yeah, I'm going to go with that. Is he successful to have a movie date? Well, he's less likely. Neither, both are equally likely. Is it a 50-50? No. All right, great job, great job. And it's kind of fun. Maybe you can start talking like this at home. I'm sure that's going to annoy your family, but start talking about probabilities. Is that more likely to happen? Right? They say, Brian, go take out the trash. Is it less likely I'm going to take out the trash, or more likely? And then your mom's going to tell you, go take out the trash. All right, so Rory, Phil, and Ricky are competing in a golf match. Their probabilities of winning the match are as follows. So P right here, whenever you see something like this is really saying the probability. And what's in parentheses is what do we want to know? What probability of what? The probability that Rory wins. Well, the chance is 20%, or that's 0.2. The chance that Phil wins is 0.05, or we can say 5%. And the chance that Ricky wins is 3/4. So we're using all of our math skills here, which is 0.75 or 75%. All right, so if we're on that little chart again, 0 to 1, and we have 0.5 right here, 0.75 is going to be here, 0.2 is going to be here, and then 0.05 is going to be here. So what is more likely? The closer you get to 1, the more likely it's going to be. So who's most likely to win? Well, if you said Ricky, well, he has a 75% chance of winning. I'd take that any day. That's really good, actually. That means out of every 4 games or matches he wins, 3 of them. So let's make sure we hit it right here. All right, I got Ricky. Check it. What? Oh, I wasn't paying attention. I got to put them in order from least likely to most likely. So who's least likely? Phil is least likely. Rory is second, and then Ricky. There we go. Wasn't paying attention. What I tell you, always go slow. Reread the questions, because on the MAT test or GMAS, I just threw away points that I knew the answer. All right. Simone is stranded on an island. That's awful, Simone. Feels like we're all stranded on an island right now. The probability of her finding safety by waiting for help is 1 out of 4, which is a 25% chance. How do I know that? I do 1 divided by 4, and that gives me 0.25, which is the same as 25%. The probability of her finding safety by leaving in the raft is 0.32. Now, if we're doing that 0 to 0.5 to 1, 0.32 is right here. First of all, let's just make sure here. You're stranded. Yeah, that's never good. Her chance of finding help if she stays on the island is 25%, which is pretty low. If she leaves, it's only a little bit better, but it's still less likely. Is it more likely than staying? Yes. All right. Is it still a good choice? Probably not. So which of these answers is more likely? So I'm going to read it this time. Simone finds safety by waiting for help. Simone finds safety by leaving in her raft. Neither. Both events are equally likely. Well, they're not equally likely, right? They're not. They're close though, but they're not equally likely. I don't know. I know mathematically she should leave the raft, right? She has a better chance at finding safety. Now, if in this real world situation, how much is the risk? All right, that's the choice you have to make. But let's try this. All right, good job. All right, I'm not even paying attention. 4. Aaron, Elizabeth, and Anna are playing a game. Their probabilities to win the game as follows. So we've already done one like this, so you should be a little bit better. The probability that Aaron wins is 0.3, or you need to start doing this in your head. If you're having trouble turning a decimal into percent, you're just going to multiply it by 100, and that's going to be 30%. I'm not even sure if you can see that. All right, so 30% right here. What is 1/2? Well, that's a coin flip. That's a 50-50 or 50%. And if Elizabeth wins, we already have it's 20%. So who is most likely to win? Well, the coin flip, Anna. Who is second most likely? That's Aaron. And who's least likely? And the reason why we're doing this, we're going 0 to 0.5 to 1. So we have 0.3, 0.2. And so I'm just going to write this. This is Elizabeth. This is Aaron, and this is Anna. So I got to put these in order from least to most likely. Least likely is Elizabeth. Oh, got to change that. Elizabeth. Aaron is second most likely or least likely, and then Anna's supposed to win. There we go. All right. Now the probability of it snowing in eastern Canada tomorrow is 0.4. Now by itself, I'm not really thinking much about it, but so if we sit here and we do the chart that we've been writing. Remember, this is a guaranteed sure thing right here, and this is impossible, won't ever happen, and this is a coin flip, 50-50. So 0.4 would go about right here, 0.4 right here. And then, so the probability of snowing in western Canada tomorrow is 2/5. Now again, they're trying to make us do our fractions. 2/5, easiest way to do this, I'm going to multiply this both numerator and denominator by 2. That'll give me 4 over 10, which is the same as 0.4. So you're going to realize that the odds of it snowing in eastern Canada tomorrow are the same as the odds in western Canada. All right, so I don't know of any meteorologist that says the odds of it snowing tomorrow is 0.4. They will say 80% chance of rain, 50% chance of rain. You hear stuff like that, 10% precipitation. They don't just say 0.4, they turn it into a percent. So there's a 40% chance of rain tomorrow in eastern Canada and also in western Canada. So both events are equally likely because they have the same probability of occurring. All right, and actually, you're not even thinking about it, but the meteorologists use this probabilities all the time. How likely is the weather to be what it is? On the weekends you want it to be sunny so you can go outside and do your thing. But you also, if you're trying to plan something, maybe you're going on a backpacking trip and the weather's supposed to be bad, you want to make sure it's accurate. All right, we've all been on those things. There's going to be a 100% chance it rains tomorrow, and you decide to stay in, and guess what? It doesn't rain. Bummer, right? And then you've had those other things saying it's going to be beautiful when you get out on the trail, and it's absolutely nasty. All right, so we got two more here. I feel like y'all got these now. We should be good. Carl is wondering if the train he is riding home from school will leave early, on time, or late. I never thought trains left late, but who knows? The probability are as follows. The train leaves early, well, 25% chance. That's awful, right? You get there on time, it's gone. Train leaves on time, it's going to be a 35% chance. And again, if it leaves late, well, that's a 40% chance. So Put the following events in order from least likely to most likely. So what is least likely to happen? Again, if you need to draw this little chart here, do it every single time and put them on here, 0.25, 0.35, and zero point 0.4. So least likely is that it leaves early. Let me get out of here. Second least likely is that it will leave on time, and then most likely it'll leave late. Is that good? I've only ridden on a few trains. I guess they left on time. I don't know. Harry and Larry, great, are having a barbecue dinner. I used to have friends named Keith and Heath. Not even that, they were Keith Beers and Keith Spears. I didn't know who they were. I just knew those names. It took me a while to tell the difference. The probability of Harry staining his shirt during the dinner is 1/5. That guy needs to put a napkin right here. All right. The probability of Larry staining his shirt during dinner is 15%. So the easiest way here is what is 1/5 as a decimal, and you can sit there and put in your calculator. 1 divided by 5 is 0.2 or 20%. So is 20% higher than 15%? Well, of course it is. So who's most likely to stain their shirt? More likely to stain the shirt during dinner? It's looks like it's Harry. Be careful. Probably don't sit next to them, because if they're staining their shirts, they might be spilling stuff everywhere else. So the question is, which of these events is more likely? Choose one answer. And so we're going to go and say Harry stains his shirt during the dinner. We're going to go, oh, there we go. And that is it, guys. Reason you have this comparing probabilities and another one about flipping coins and the dice, and you should be good on that because you did the activity where you flip the coin. I just wanted to have a reminder and a review of it so that you can get out what you saw and make sure you understood theoretical and experimental. But yeah, y'all have a good week.